Okay, so yeah, welcome everyone to our online audience, but also welcome to the present on audience as well. Today we have our lecture 3 in the Cloud Computing and Big Data course. It's about Apache Spark for cloud applications. So who of you had heard from Apache Spark before? A little bit, okay. Apache Hadoop per se, all related a little bit. MapReduce maybe, it's another sort of paradigm. Of course, you all should heard about this in the prologue, right? So, but still, you know, we talk a bit about the underlying layer today that we missed out the last time. If you remember in lecture 2, we sort of did already a bit of machine learning. We thought about, okay, logistic regression for binary classification and so on. So let's dive directly in the review of last lecture before we dive into the material of today. And the last time was really a moderate introduction to machine learning. So basically no prerequisites were needed, a little bit of maybe mathematics and, you know, some laws that you know, but in general, I hope all of you had a little bit of an understanding what now classification entails in machine learning. That means you have a sort of given class setup of, you know, your data, which is here explained by the couple of dots in green and red. And then you basically have a new dot coming, right? A new data item, and you want to classify is it this or that class. So admittedly, very simple machine learning problem. In our remote sensing research, we have up to 50 classes, right? And up to 200 features with different bands in the earth. So really interesting data sets, but to understand machine learning, it still captures the essence, how you do it, basically. And we thought there are always like 3 ingredients that you need when you think about machine learning, right? So you would say there should be some pattern in the data. Hence, a random number generator to learn, you still can do it and try to learn it, but it doesn't give you any insight, right? Second, then there should be no exact mathematical formula. You can still do machine learning, but maybe it's better to use already the mathematical formula if it would exist. And the third is, of course, this thing that you cannot live without, and this is data. We started with the interesting Iris setosa and Iris virginica setup, if you remember a little bit with the flowers here. 2 classes which, you know, seem to be pretty clear. But then we also had to admit to ourselves, and looking on this new picture that was coming in, we were not exactly sure if it is a Iris setosa, Iris virginica. Hence, we have to think about features in the data. This is a very important term in machine learning, learning from data, learning from large quantities data. And we learned that the petal and sepal width can give you insights a little bit by analyzing this. And luckily we had labeled data. So some people have already given us the classes where the label was Iris setosa and Iris virginica. Then over the course of the class, we basically introduced a little bit this simple perceptron learning model. It's the simplest in the learning models, if you will, and still basically used today in a neuron in deep learning networks. Of course, on steroids with new activation function. But one key theme remains that you have gathered several inputs into basically the idea of the neuron and then sum them up linearly using weights. And this weights is, of course, the loaded item we want to learn, right? So, and this brings us also to different hypotheses. That's why they're both here in red. That are things we don't know. We know the sign function, yes. We know basically the X, that's our data set, right? So sepal, petal, and so on, the width. For mathematical convenience, we also have the bias, if you remember from the line, the bias incorporated in the learning, and will become also learnable parameter. And for another mathematical convenience, you can write it as a dot product, or here as I did with W transpose X. What now the algorithm will do, so this is a learning model. It doesn't say anything about the learning yet, right? This is a learning model. How we learn it is now apply an algorithm, a learning algorithm, right? Hence, many of these models come always with a certain distinctive learning algorithm. In our case, it was, of course, very clear the perceptron learning model, and there's a perceptron learning algorithm. Actually, the PLA also coming from the same authors, which then essentially just was very simple of adding or subtracting a vector. And over the time, and this is inherent in all the machine learning problems, you have an optimization problem or an iterative approach to the solution. You go over and over and over again through the data. Later, we will call that epochs in machine learning and so on and so on. But let's stay with a simple idea here now in machine learning. And by doing so, we can always, of course, with a supervised learning setup, check if the label is correct. right? So we have given data to us where we know already this new flower is Iris setosa or Iris virginica. And by doing so, it converges if the data is linearly separable, right? What was this for an interesting term? That is also something you should know. If here would be one green dot somewhere in the deep of the blue space, the data would be not anymore linearly separable. The other way around, the blue in the green space, same way. So it's a very trivial algorithm, a very simple algorithm, not really works in practice, as you can imagine, and there have been many modifications to it. Still, the whole idea of machine learning should entail basically this problem. And then we had this simple idea of encoding Iris setosa and Iris virginica as -1 + 1, right? So we said, okay, these are for mathematical convenience transformations. That is no harm done. We still have the differences in the classes. And this is why we use the sign function to determine then basically if it is now correctly classified or not. Now, we had also seen then in the later parts of the lecture, and that's where we use the first cloud service really now, which is sort of a questionable cloud service, because today we will unreveal a bit that, of course, the scalability of the Google Colab is extremely limited, right? It is a cloud service. Of course, it's in the web browser. You don't have the computing on you locally, but it is basically a sort of very limited approach how you can do Spark in the cloud, and we learn more about this today. However, we have seen with a simple learning model, which is basically a linear in weights, that's why it's still a linear learning model, we can still use basically the regression, the real value of it that we got out by playing around with these weights and put it to another function, which was then here basically the logistic function, which squashes everything between 0 and 1. So again, for binary classification, for us, a good indicator of saying it's this or that class based on how close we are with the mathematical numbers, right? And this basically function then gives us a clear indicator if it's this or that class, or basically how you end up here on this line, what you can see. So often in machine learning, you will also see that the algorithms will be not extremely accurate, right? There will be probabilities inside. We learned about this about more. Hence, you have here a certain probability of going to the class 1 or class 0. Still, usually it is basically correct. Today, we will tackle then exactly this, what you see here. The question is still, is this a basically scalable solution? And what is now the difference of using MS Azure, AWS, and so on? Hence, today will be really of using Apache Spark, and we learn a bit more of the underlying idea, PySpark, Spark kernel, or what we left out a little bit last time, because we wanted to focus on machine learning. We wanted to focus on understanding first this idea. And now we basically put the lower level into perspective. And also this is directly related to your assignment 1, which will be handed out on Thursday, where you will use an HD Insight in MS Azure and can basically use your cloud in a real fashion. Of course, you also should have a little bit of an understanding of collaboratory. So one of the first tasks would be to reproduce a bit in the Colab, but then we go to the HD Insight cluster. So today is therefore a very basic introduction to Spark. I think just get generally why it's big data analytics. You know already the difference between big data analysis and big data analytics from the prologue and the lecture 1. And also some elements of Apache Spark, which makes it now so scalable, right? Firstly, that means, again, touching on distributed computing on some level, but also thinking about the data. And we're not losing sight of some important aspect where we would say the performance. And there's something called Apache Hadoop, but we will introduce this later in the course, and MapReduce. As you remember, normally in the normal flow of a course, I would have given that already, but we want to give you something early to work on the assignments. But essentially, these are all very interrelated. Hence, there's something which was there before, Apache Hadoop, basically providing also a file system, which is quite relevant, Hadoop distributed file system, which sort of has Spark on top. And we have to talk about the parallel performance, specifically because it's very expensive in clouds, and I will make the point for it, right? So we review the costs in AWS when you want to have a very good Spark application, which means memory. You remember from the introduction, we talked about the memory hierarchy. The more you go up, memory is where the money is. And this gives you sort of super performance in Spark. But of course, as a startup, you always have to pay the price for it. Do you really can afford it? Do you need that speed? Or maybe we can just do it overnight and compute something. So this will be all something which we do in part 1. Part 2 will be then looking more on applications and the different areas where Spark seems to thrive. right? Some of them is really combining it with different SQL, I would say, open source framework. There's Presto, there's Hive, there's actually quite many of them. And the Spark has a library for this SQL, which we will talk about. We in the course here and there touched already upon the machine learning library, MLlib from Apache Spark, but also there's a streaming library and graph library that exists. So we will review a little bit the graph library today, just as a kind of nice incentive of the iterations again, how you can have a very simple problem, like for instance, the popularity of websites, like PageRank algorithms and so on, really phrased as a graph problem and then as actually computational quite expensive. Okay, we have here some video, maybe, hello. Then we have also then at the end some examples for you prepared in Spark and business applications, of course, some videos again, and we'll again review a little bit the runtime all the time with the PySpark that was there. With this, we fulfill also quite some promises. You see that here on the right-hand side. So I was, of course, forward referring a little bit to Apache Spark, will be explained in more detail so that we have a basic understanding of machine learning first. So let's say about Apache Spark, you can see it as 5 key elements, which is not completely true. There's something also underlying, which we will discuss in a moment. But looking at Spark itself, essentially you have this 5 core elements, which is really the Apache core element, which we have here now the focus on. And then this different areas where we said the applications that use these libraries. Now, the benefit of providing these libraries is that everything is already prepared for a distributed computing fashion, right? That's where now Apache Spark is striving a lot. So it's really distributed computing at scale. So this has an inherent engine to work on these problems of sending tasks and to different executors and so on. And we will motivate this again and again when we come off different scheduling elements and so on. One respect, however, we should also mention the data, right? So if you remember, big data analytics was a little bit of thinking, let's accumulate data and compute where the data is instead of, doing a lot data transfer and putting that all to a high performance computing machine, compute it in high performance and getting it back, right? So saving data transfer and so on. So there's something related to that you also need an underlying layer here that we basically miss out in this graphic a little bit, but we will talk about in the lecture again and again. Hence, you would have something like the Hadoop distributed file system, for instance, which is one part of the Hadoop system, which really is an interesting tool set that is underlying Spark. But of course, depending on which cloud we go, to AWS services in the Amazon Web Service, we would have S3 interfaces, blob storages in Azure, and so on. So there could be very cloud-specific vendor-like, basically data solutions as well. I should mention this is all open source, but installing Apache Spark yourself and installing Zookeeper, I will make a point what Zookeeper is, installing this together maybe with Mesos, with a resource manager called Yarn, and so on. This is not an easy topic. So having this appliances in cloud is some benefit. I can assure you that. I was installing Spark on HPC clusters 7 years ago a lot, and it's a lot of obstacles with it. So having this, let's say, appliance from clouds is something very attractive, but we will also see you have to pay the price for it if you do it in the cloud. Hence, there are these 2 elements in the course here around this technology. And I will focus today more on the in-memory processing. Everything when we come to the distributed processing with MapReduce, Hadoop is a little bit out of order so that you can start already on the assignment, while we will catch up with what is MapReduce exactly, what is a distributed file system, HDFS, the benefits. That is all coming lecture 5. Combined, of course, with virtualization. I said the cloud is fundamentally actually fueled with virtualization, which I will cover in lecture 4, while you do already your assignment. But these are all conceptual topics which are not so relevant when you do your assignment. That's why we save some time there. Hence, today, the memory is really something we have to sharply look at, and we will do. And by doing so, you can already see a little bit, although both technologies, Hadoop and Spark, are optimized to work on terabytes, petabytes on data, so large quantities of data, big data, Hadoop is still very much slower. For instance, if you have a logistic regression here, something similar we did with binary classification in lecture 2, you see that Spark is much, much, much more faster. And we want to understand why is that the case. And hence the in-memory is something, of course, which is important in that. So Spark itself is now really broadly deployed. So you can imagine also when you Google that, Apache Spark has now been used by many different companies, but not all of them have a production in-house deployment. So hence, still many use also the big public cloud vendors like MS Azure, AWS, with the EMR service, the basically Elastic MapReduce service, or even the Google Proc, which is also in the Google Cloud, basically installation around Apache. And when I say Apache, this is loaded because you will see that Apache Spark lives in a bigger ecosystem. There's HBase databases, there's data warehousing, there are lots of different solutions. And this is usually not so easy to bring them all together to operate. Hence, again, for many even of the big people out there, and we will review some of them in this lecture in the second part, it's still maybe better to really do this and basically see how we can improve by not having, let's say, an in-house solution, but also using the public cloud vendors better. Of course, this means you don't have to have something like sensitive data. We talked about this. This was one of the motivation of using public and private data clouds, for instance. And this is something what would be also very much supported by the setup. Initially, that was an open source project, hence from Apache, getting an enormous developer community these days behind it. And it enables you to get also to this idea of actually creating then, if you need really big, large directed acyclic graphs. So this means the tasks that are depending on each other form a sort of tree. And the acyclic notion is that you basically cannot go up in the tree anymore, right? So it needs to be separated. That is an important assumption when you go extremely distributed, because otherwise you have to do lots of rollback of computing if there are dependencies reintroduced actually on the top by doing so. And it has also enormous data sharing capabilities. One of them is, for instance, the RDDs, which are traditionally there. Today, there are also data frames used. So there are different concepts how you do it with data. And one key theme that is also staying with us now is to have really a head node. You would say that is the head node here, having a driver program, nothing else than having created a Spark context. And you see that in the first initial lines in the Jupyter notebooks we did in lecture 2, for instance. And this will all become a bit more clear when you do assignment 3.1 and lecture 3.1 with it. Assignment 1 based on lecture 3.1 when I demonstrate a bit again with these points. Then you have the cluster manager, which does the scheduling of all the different tasks that you want to basically bring to different worker nodes. And this is a scalable aspect here of it. While the head nodes are usually 2 for resilience, basically for fault tolerance, if one head node goes down, the other one lives, because sort of a manager, I will come to that also in a moment, you can scale up and down the number of workers you need, right? And this is a key paradigm now of Spark, making it scalable. And you see the many arrows here, that means it's quite distributed, in fact. So there are message exchanges, but the beauty, and that's why I bring this example here on the bottom, is now you don't feel the remoteness. And this in the programming style, the way of programming. While in MPI for high performance computing, you really have to know which communicator to use, which cores to address. You're very much low level, right? It's very communication library you have to use. Here you focus maybe on error message analysis, and you have very simple, let's say, simple commands to filter here. For instance, you see that on the text file, firstly, with this function, everything which starts there or contains error, and then you split them up and map them and can get very quickly to something you see here, which is then the execution graph on the bottom, taking some data from the HDFS, hence the data for the error logs, filter them, and then have a basically mapped idea of all the error messages. And here it will be, basically using the Spark and the Spark context, and will be scheduled on all the workers without you knowing what would be here now actually where executed. And this is one of the benefits of Apache Spark. So in a way, it enables you a very high level of parallelism that you as a user don't really need to know, right? So someone configures, let's say in your company, a cluster for you in MS Azure and Amazon, and you as a machine learning or data analysis guy basically can just use this cluster with simple Python programs. If you remember lecture 2, we did a lot of commands, but we never said, well, this core or this worker, please do this, that other worker, please do that. So there was no load balancing or something which you rather think in high performance computing. Again, a notion of contrasting it to high throughput computing again. Then we come to an idea of a bit more closer look how that works and the possibilities you have, right? So the interesting thing as open source project is that the people have extended it in all sorts of directions. So you can have it as a local thread manager even. That means a cluster manager, instead of working very distributed here at scale, can be even maybe in a way run on your little laptop without big benefits, you can imagine, because memory is limited and the cores is limited, but essentially there's a possibility. The key is still to have the Spark context to create it. And this will then drive basically the task to the cluster manager and these executors, which will be then spawned on all these different worker nodes. But this is all pre-configured when you already have the cluster. And we will come to this when we, for instance, look at the HD inside. Now, what's really happening then by the idea when you define the work is that you have this interesting idea of programming it very, let's say, without having any parallelization in mind, right? You would think, okay, I do some join and group operation, which ones, it doesn't really matter, but it sort of films the directed acyclic graph. But the scheduler, of course, has now to do the job and to detangle this all. But this is happening without you knowing really, right? You give it to Yarn or you give it to, Mesos on a higher scale, and it will create the parallelization for you and break up this interesting tree in this different chunks of tasks that can be now actually, as you see here, for instance, executed in parallel, right? That was the same idea here. There seem to be two objects that are, not dependent on each other. Let's have them in parallel computed before we join the results with these tasks and then come to the final solutions. That is now the real instruction set that is Spark using without you knowing. You're still on your Python level. Now, what's happening one level deeper is then that the scheduler now is, of course, breaking this to different executors on the worker nodes, right? And this according to the idea that you have here in this, scheduling graph. However, it means also it will wait when, for instance, here, one of these tasks that you see here, there are two, right? One of them will take longer. We cannot start the second one, right? So there are dependencies on this. That's why it's this graph level idea. And all of this is basically configured or basically done by the interesting driver program in collaboration with the cluster manager that then actually performs the execution. And there are two, let's say, main notions, transformations and actions. I bring them still in, although many people work with data frames and pandas and so on, because they capture a certain essence, what you can do now with the data. Now, when I say way of programming RDD, I think about transformations, the word. Right, so this is now important to understand all these different examples. Again, simple examples, but they will already parallelize a problem and making a domain decomposition, let's say on this area of 1, 2, 3. And then you would say you will just have everyone who is in this nums area, two squares, and you put it to a function. And that is a function you can define very easily. You see a modulo, you see to the square. And what's coming out then is basically 1, 4, and 9. Right, so this is now in squares. And when you then squares and filter, we filter here on modular, right? On these squares, we see only the 4 will basically survive, right? And so it's very simple ideas and transforming the data without you basically thinking about any of the parallelism scheme coming about. And then another one, which was here the flat map. This is important to understand that it's here still on nums, right? So this is here on top, saying we have a range until -x - 1, which means here until 2, starting from 0. So that's why we have a 0, 0, 1, and 0, 1, 2 for the 3, essentially. Right, I hope these examples are clear. I mean, it's still, let's say, showing you that this is easy programming without big parallelization. Now think about big data items, of course, where you operate all of these large arrays, large quantities of data. This can be quite enormous computing, but this is done by the Apache Spark engine. Now, when you do actions, that's a different story. There's a question, one moment. Yeah. There's a question about, so the nice thing is to parallelize it in RDD, if that's the only benefit. That's one of the benefits, is not the only one. In the name is resilient data. resilient data set. That means whenever there's an error, let's say it often happens that some computing will fail, the scheduler and basically the whole idea of this notion of RDDs can go back to a status where you can recompute. We call this fault tolerance, which is inherent in MapReduce, but also basically in Hadoop and Spark. And this is one of the key benefits as well. So essentially you could say that it's a very, let's say, robust technology. You know, in MPI, that would be not done in HPC clusters. When you have an application, one core fails, one execution fails, just let's say from 100,000 cores, the whole application is dead. You have to recompute everything from scratch. So what RDDs have the benefit is, and it's a good question, coming back to a certain status in the graph, as you have seen, that has been not done, and roll back all of that and has all the functionality in the Spark core to roll back and recompute in another task, in another executor, right? Because this executor will be then marked as malicious, right? Because it's all distributed, could be many reasons, you know, firewall problems or the server is down. So you try to get to the executor, but the executor is not existing. So it would try then another executor from the scheduling pool. And to support that with the data structures, all one benefit also of the RDD. But there are many actually data structures used today, I have to say. Coming now a little bit then also to, which is very close to it actually now, to the idea why we use this resource manager, Jan, for instance. And actually, you know, Achim, just a bit personal notion, Achim is one of the, let's say, he was doing lots of research in resource management systems. So you can talk about him. He knows about resource management systems, Slurm, and so on. He did his PhD in it. But this is on a sort of a little bit higher level than HPC, where we have also resilience in, and where we take also a little bit more the notion of data in, right? So, well, in message passing interface and high performance computing would send data a lot, send, receive messages. Here we think about the data is already there. And you see that a little bit with the data nodes here. So we say there's some interesting, let's say, word count example here, right? Which we have as a client. But the idea of the data is somewhere stored already in different blocks, distributed, right? So there's already something which the HDFS is providing us, replication of blocks, distribution of blocks of data. Let's say you have a 1 petabyte of data and you want to do the word counts on it. So this will be distributed already across to the Apache Spark and Hadoop engine. And what Jan is basically doing is now, as a resource manager, to check which are actually now actually have this data, right, together with the head nodes, and then also who has the capacity to really work on it. Hence, it is responsible to really now use this different worker nodes, right? In Hadoop, which is a bit more like here with MapReduce very specifically, while Apache Spark can go beyond MapReduce, has also other ideas at hand what you can do. And by this, it is basically distributing it, collecting it, and it also ensures that no one intervening from other users, right? So it's also something, think about multi-tenant use. Another indicator here, I just wanted to bring you back in this, that here's of course a cache. If you remember, cache is important with memory, right? Hence, for Spark, which is very cache aware, doesn't take only data locality in, but also uses a cache in the worker nodes significantly. Hence the benefit of the memory we will look at. So you see, it's sort of an interconnected jungle of different technologies. So we have Hadoop, we have Yarn, we have Apache Spark. So they will all come together, and we have even the Zookeeper coming in a moment. So it's quite an interesting situation if you have to set up yourself all of this. Hence, we will look as an example here, MS Azure HD Insight that you will also use in the course, and actually how that is generated so that it's a nice user experience for you, right? So we have, again, the Spark core with the different libraries that you may want to use for applications. We discuss in lecture 2 a little bit more about this level. So let's stay a little bit of understanding the core engine and how it can be deployed. We said Hadoop Yarn would be one example coming out of the Hadoop original developments. There's no harm with it. It's a resource management system, which is, let's say, not as advanced as those in HPC, but still does a job and distributed everything. But you see here, it's basically part of the head nodes, these 2 head nodes that then communicate with each other and see what loads we differently want to tackle and then distribute with all the different worker nodes. And here you see also now the important aspect of the HDFS we have to talk about. So, because if you always read from data, right, this is expensive. Read from real data sets on the disk. That is expensive. What we have the idea is, of course, leveraging, as you see here, with the task, hopefully the cache as much as possible. So you would to co-locate the same task again and again on the same data because it's already in cache on the same worker nodes, which is an important concept there. Now, going one level bigger in a big, let's say, in a really big cloud data center operation, you would say that you need something bigger because you would have maybe different Sparks at the same time. You would also have network aspects, right? Not everybody should access your Spark. Now, there would be HTTP ports open in the cluster. So there would be certain gateways that needs to be configured to protect it. They have a better graphic on this in a moment. Hence, you need more services to check. You will see there's also a zookeeper coming in. And Mesos is a sort of more coarse-grained scheduler than on top, keeping basically together your whole cluster setup, right? Instead of just this small Spark core, which is then deployed, maybe using Yarn and others. With Mesos, you go one step bigger to basically use it in a real data center operation. And we will review this a little bit when we talk about Zookeeper as well later on. When we now think about the benefits of using memory, I was alluding to this a little bit when we think about HDFS read, right? How it was in Hadoop over many years before Spark was developed. Basically, you have always this very slow iteration. And why I talk about iterations is to make the point back to logistic regression, right? When you set machine learning algorithms, they are always iterative. They go back through the data. Hence, the data was already in the cache, in the memory. And you can apply some optimization on it. Could be the weight updates we discussed. It doesn't matter in the moment. Basically, that's the point. You always work on the data again, per iteration. So this is very bad for disks, right? If you just do read and write from disk and ignore caches, ignore everything. So this is a bad thing. So we see here quite clearly Apache Spark and also the documentation of MS Azure has a very good idea here. In Spark, you hopefully read once in a way, and then you basically can directly from cache go again and again to work this. While in other words, in MapReduce, you always have for the map and reduce operations, read and write, right? So reading for getting the data in, do the weight update or doing something on the data and write. So this is then one of the performance benefits of using memory. I think, are you with me so far? It's sort of understandable, right? Now, what we have to see is, of course, we go here and pay the price. Now, when you here now compare Amazon Web Services, right? And they have an equally service like MS Azure that we're going to use. We just cannot use everyone. So they have a sort of elastic MapReduce, very similar like HD Insight, I should say. So you have to steer which of the resources you want to take for this cluster. And you can see quite clearly here on the top of the scale, if you really want to have lots of memory, we talk about an hourly rate, right, of $100. And this could quickly mean for an SME quite substantial money. Of course, there are moderate solutions. Not everything is $100. You can do a large appliance. And these are now the types of really metal, so to speak, that you have underneath, right? The real power of the resources. It's still okay. You maybe have reduced memory and you can still afford maybe $13 per hour. And this is already memory optimized. There's some in the general purpose category. And no matter where you go to which cloud, you will see the same scheme, right? In the Google Cloud, in the in MS Azure, because of course memory is expensive, right? And this is a key idea now. However, when we want to leverage Spark on this, we need that, right? If we want to use, here's the example that I was alluding to, Amazon Elastic MapReduce, same setup of actually elements, Hadoop, Spark is there. There's also Hive for SQL databases and data interactions like Presto as well, that are managing the distributed SQL queries very well between different data sets which are distributed. In the moment, it doesn't matter, and we come to that a bit back when we do lecture 5. Just take away the message that, of course, all the big cloud vendors are talking about Apache Spark and also have similar solutions. In lecture 2, we were using a little bit the Jupyter Notebook. You see that here. Also, the Elastic MapReduce in Amazon has also a Jupyter Notebook solution. So in a way, things are a little bit portable once you're on this level of Jupyter and Python and can try to basically, go between the different, cloud vendors. And this will be important also in the assignment to check a little bit, just a couple of terminologies before we conclude the first part. We have learned about Yarn. That's a scheduler now, basically. But we still have to do a kind of idea how we now link this to the application, right? We still want to interact with the scheduler. We want to interact with a session that is created by the scheduler. And this session is now loaded, and underneath will, of course, do the distribution without us knowing. And this is an important part, because while we do this part, we do it distributed, while we still in the Jupyter Notebook do everything very nice and shiny. However, in the assignment, you have the opportunity then to see a little bit more the distribution of it. So when worker nodes really have to work, something we didn't see in the Colab, because Colab was not really distributed. It was remote and has a PySpark kernel, which is local, using essentially just one resource, right? And this is something I will also look into assignment 1, and then of course in lecture 3.1, demonstrating you a little bit more. Then this is an important concept, which now enables us that as a user, I don't care about this number of worker nodes even. I can call the guy in the, my CTO and say, I need more worker nodes. This takes too long here. And he can adjust and reduce depending on my need and those of the whole company without me also changing the code of the application, right? The scheduler here, the application context of the session, and then the Spark context that is generated out of this. You see that here, the Spark will be then the core where we start every operation from. That is the Spark context, the Spark engine that is really then there, which is located in a way, if you want, at the head node. And whatever we do, logistic regression, a fit derived from the session, will then start of distributing it using the power of the cluster manager or the resource management system. So, and this, in a way, is how the cluster operates. I just wanted to add one more thing before we break. And this is the idea of a zookeeper. So someone has heard from Apache Zookeeper, maybe? I mean, the name suggests already what happens actually when you have lots of different open source tool sets working together. It's also coordinating hell a lot of things. For instance, if you have now 2 head nodes, it has to be, also thinking about, this looks good. The head nodes is having, let's say, all the idea of the load, but there are 2. So they also have to coordinate their work, right? So in a way, you can see it as another higher level service that coordinates tasks between the 2 head nodes, between many other activities that you see also here. I was alluding to the gateway, right? And the security elements in it. You think here as a HD Insight cluster that you generated, and we will see how we generate this basically in the practical lecture 3.1. I demonstrated to you there. So that means we have to see, okay, we pick here 2 head nodes. You see here how that works in MS Azure, for instance. The Zookeeper nodes are always fixed on 3, but nicely they are free. And then the worker nodes, you see that's editable. So here we can now do 20, 30, 40 of a different kind, but then you will see also quickly how the total estimated core hour per, amount per core hour will quickly rise. And of course, you can change also to better hardware here, right? So the more expensive, the more memory you can imagine, the more you pay per hour. And the Zookeeper is then also helping us with all the different services, because inside these clusters are, of course, now many people generating HD Insights. It's not just you, right? Many people have HD Insights, tons of them next to each other. And when you operate with these different services, they have lots of HTTP ports for communication, interactions, and so on. And this service keeps track of lots of these ideas on a so-called higher level, if you want. So this is how Azure works. Maybe just some alternatives for RDDs. Very popular, we have seen in lecture 2, just to come back to this. Data frames, pandas is also quite nice. They're a bit more schema-oriented data sets, but still can operate remotely. So of course, also having some fault tolerance inside, which is also more and more used today. You have seen that, and we'll see that also in lecture 3.1. And I think I stop here the video recording, but I have an interesting video maybe, which is a little bit outdated perhaps, but still captures the essence of the remote execution in Spark.